All right, guys, this is a quick podcast on design to get you familiar with calculating the height of a pyramid when all the key vertices in the pyramid are defined via position vectors. All right, guys, let's start with the simplest case, and that's the case where the base is aligned with the XY plane and the vertex is aligned with the Z plane. So in a physical scenario, it might be that the positive X points in the east direction, the positive Y in the north direction. So you've got your compass bearings in terms of I's and J position vectors, and your K element captures directly the height or distance that it rises above the XY plane. So when you've got, say, 4 points, 4 vertices, O, A, B, C making up the base, and point V marking the vertex of the pyramid, it's pretty obvious what element is captured by the height. So just picturing each of those 4 points placed on the plane, so O, OA, so OA a multiple of I, OC a multiple of J, and OB each of those 2 elements. So obviously this is a rectangular base pyramid. What would be the height in this scenario? Because the 4 vertices are aligned with the XY plane, it's simply the multiple of K. So this is clearly a 4x6 rectangular base pyramid where the height rises directly above it and the height is captured by the multiple of K. All right, in this scenario, we've also got ourselves a quadrilateral based pyramid. You can see the 3 of the points that make up the base, and then there's the origin. They consist only in terms of I and J components, and so hence they're all coplanar. So as is the case before, the 3rd point has the additional component of a K component. The multiple of K is 6. So what is the height? The height is equal to 6. Okay, so this is again straightforward. The fact that it's not a right pyramid, that is the fact that our point D doesn't rise above the dead center of the base OABC is not relevant. The fact that B, C, and D are all IJ multiples and O the origin, and whereas OD has that multiple of K, that's enough to appreciate that the height of this pyramid is indeed just that multiple of K as it was before, even if it's not right. Now, interestingly, the base of this pyramid happens to be a rhombus. So if you want to, you can go and confirm, given the position vectors OA, OB, and OC, just go and confirm that that's indeed a rhombus if you wish. All right, so here's a scenario, in fact, no different to the ones we were looking at previously. It's also a pyramid where you've got a pyramid OABC being the base and V being the point that's not on the same plane as a point O, A, B, and C. But interestingly, in this case, the plane we're talking about consists of the XZ plane, because what we're talking about is multiples of I and K only that make up our points A, B, C, and the origin. So in fact, it lies on the XZ plane, and in fact, the point that's not on the plane, the point that's not coplanar with the other 4 points O, A, B, and C, is this V, and it's got a J component where the other ones only had I and J components. So in exactly the same analogous thinking, we can clearly just determine the height of the pyramid to be 5 without any further calculation. So it's a pyramid. You might want to spend a bit of time working out what type of pyramid. Of course, you can see clearly the multiple of I and the multiple of, hang on, let me just get this pen out of the way. The multiple of I, the multiple of K, they're all of equal length, so it must, and they're aligned with the positive Z and positive X axis, so it must be a square base pyramid. But the height that square base pyramid of side length 4 rises above the base is 5. The fact that it's oriented in the manner you can see doesn't matter in the slightest. Square base pyramid, side length 4, and height 5. Okay, determining the height of the pyramid and indeed the volume of the pyramid, which is 1/3 times area base times height. In the last several examples was pretty straightforward. It just turned out to be a multiple of k typically, or a multiple of the other one of the 3 unit vectors that wasn't previously expressed in the identification of the other 3 points. But this is a case where our base OABC is not aligned with the XY plane, is not aligned with the XZ plane, is not aligned with the YZ plane. You can see OA, OB, and OC are multiples variously of I, J, and K. So it's a skewed positioning on the XY plane, okay? And D is some point running above it. So we're in this particular scenario, vectors OA, OB, and OC are all coplanar, are all linearly dependent, and OD is a vector that is not coplanar, is not linearly dependent. But what our aim is here, our task is, our challenge is to find that the height, the distance that D rises above that skewed base OABC, and there's a beautiful technique involving scalar resolutes that'll get us there. Okay, if you get a question like this, you're most likely going to be led through the solution process through an extended response format. First thing, no matter which direction it leads you in, it's going to come up with asking you to find a vector that runs perpendicular to the plane OABC. Now, without a lot of prompts into how we're going to find that vector, let's just think about the ways in which we could conjure up such a vector. So the first thing to recognize is vectors OA, OB, and OC are all coplanar and hence linearly dependent. So OC could be described as a linear multiple of A and B, etc. So that's interesting for where we're going next. I might refer back to that in a minute. So how do we find this vector that runs perpendicular to the plane OABC? So first things first is let's just let U be such a vector. So the coordinate triple XYZ and position vector from the origin from O to that point U, XI plus YJ plus ZK, let's assume is a vector that runs perpendicular. So let me just draw it. So such a vector. So here's my X, Y, and Z, and that's a vector that runs perpendicular to the plane OX, so OABC. All right, so here we are, here's the point. Now, if it does indeed run perpendicular to OABC, it means when I do the dot product with OA, OB, and OC, the result should be equal to 0. And there we are. And when I try to enter that, the equations that arise out of X, Y, and Z, there's 3 equations that arise out of X. If I enter that into my calculator, I get the following result. So dot product with OA gives me the first equation, dot product with OB gives me the second, dot product with OC gives me the third equation. Now have a close look at the solution. The reason why it's not a unique triple X, Y, and Z is because, as we said, OA, OB, and OC are linearly dependent. OC can be expressed as a linear combination of A and B, so I don't actually get a unique solution. Nevertheless, hold the presses. That's very, very useful information. Let's have a think about what that general solution is suggesting. It's suggesting whatever, so it's infinitely many vectors that are perpendicular to OA, OB, and OC, but no matter what they are, they have the form that whatever multiple of k we're talking about, our z component, our x component is minus 2/5 of it, and our y component is minus 1/5 of that z factor. So we are looking for just any vector that runs perpendicular to the plane OABC. So given that 5 is a common divisor, a common denominator in the two, let's just assign z the factor 5. Okay, so we're looking for a member of this infinitely large set of vectors x, y, z, xi plus yj plus zk that run perpendicular to OABC. So in the particular example where z is equal to 5, x being minus 2/5 of it will be equal to minus 2, and y will be equal to minus 1. So what have we found? We've found, so x being aligned to I, minus 2i, y being aligned to j, minus j plus 5k is one such vector that runs perpendicular to the plane OABC. And believe it or not, we're very close to being able to work out the height at which D rises above the plane OABC from there. So stay tuned. Let's just click away. Okay. So here it is. We've found a vector, a nice neat expression of a vector that runs perpendicular to the plane OABC, and we arrived at it via the dot product, and appreciating U must be perpendicular to each of those three vectors individually. So where do we go from here to work out the height of the pyramid? The answer is the scalar resolute. Okay, we're just about to work out the height of the pyramid now. So we take our vector u, it's just drawn in a small manner there, I'll just make it a bit larger. It doesn't matter what its actual height is. All that matters is it's running perpendicular to the base OABC. And so what the height is in fact the vector resolute, the scalar resolute of OD in the direction of u. In fact, it's the scalar resolute of AD in the direction of u. It's the scalar resolute of BD in the direction of u. It's the scalar resolute of CD in the direction of u. It's the scalar resolute of any vector that makes up the slant edge of the pyramid in the direction of that vector that we've found to run perpendicular to the base. So let's just work with OD because we have it directly. There's no need to create an AD or a BD or a CD from this situation. OD is given to us immediately. So here it is, if you can picture this. So here's that vector. So if I just draw, let's just change the color. If I just draw a vector, or if I just split up OD into two lengths, OX and XD, OX, the vector, is the vector resolute of OD in the direction of U, and OX, the length, the height the pyramid rubs above the base, OX, the length, is the scalar resolute of OD in the direction of U. So how is that calculated? OX, the length, is OD vector dot product with the unit vector in the perpendicular to the unit vector perpendicular to the base OABC, and we've already determined U to have the form as we saw before. Let me just bring that up on the screen. So there's the scenario, and of course U is minus 2i minus j plus 5k, and it's appealing to the mechanisms of scalar resolute calculation, and there, lo and behold, we've found the height that D rises above its base in the pyramid setup. So this is the technique you must remember. If the base of the pyramid is not aligned with the XY plane, the XZ plane, or the YZ plane, if the base is skewed in the 3D Cartesian setup. So please remember that one. It appeared in last year's exam, and it's handy for you to be mindful of it.